Morning everyone. This is the last of our series of lectures on training neural networks. Now this lecture is actually going to extend beyond the 80 minutes of this class. So I will record an extra 20 or 30 minutes after the class and post it. Now we're going to be discussing objective functions, regularizers, normalizations, and other such issues. So here is a quick recap of how we train a neural network. We define a loss function. The loss is the average over all of the training instances of the divergence between the actual output of the network and the desired output of the network in response to individual training instances. So this loss quantifies the gap between the function that the network is currently computing and the function that we actually want to compute, and we estimate the weights to minimize this loss. We use gradient descent to minimize the loss. So the gradient of the loss with respect to the parameters is going to be since the loss is the average of the divergences for individual training instances, the gradient of the loss is going to be the average of the gradients of the divergences for the individual training instances with respect to the network parameters. And so it is this term here that we compute using backpropagation. And once you have computed the average gradient over the training set, we use gradient descent to estimate our parameters. So we have seen all of this. Now, the last thing we saw was that the basic gradient descent formalism requires you to compute the average gradient over the entire training data before making a single update to your parameters. And this would require processing the entire data for each update and can be terribly inefficient. And so we use online methods instead that incrementally update the model using subsets of the training data. Stochastic gradient descent analyzes randomly drawn individual training samples and updates the models. Minibatch descent randomly samples small batches of training data and updates the models with them. In either case, we have to reduce the learning rates with iterations to guarantee convergence, otherwise these things will not converge. And the sum of the absolute values, we have these two criteria for the manner in which these learning rates shrink, is that the sum of the absolute values of the learning rates must sum to infinity. At the same time, the learning rates over the entire sequence of the entire learning must be square summable to ensure convergence. Now, so what happened? Yeah. And one problem with online methods is that they have greater variance than full batch training, potentially leading to worse estimates. And so you have to twiddle around with the mini batch sizes to minimize this variation. We also saw trend algorithms. We saw that the online methods in particular require trend algorithms because of the variance between the divergences that are minimized across batches or mini batches. And so trend algorithms smooth out this variation by considering long-term trends in the gradients, and this can lead to faster and better convergence. Among trend algorithms, momentum and Nestra's method improve convergence by smoothing updates using the mean, the first moment of the sequence of derivatives. Then you had second moment methods like RMS prop and Adam, which consider the variation, the second moment of the derivatives. We looked carefully, specifically at two of these methods. RMS prop only considers the second moment of the derivatives to normalize our update steps, but it doesn't consider the first moment. Adam considers both the second moment and the first moment. So it combines the best features of both momentum and Nestra's method. And there are various other variants of the same theme. All of them typically provide considerably faster convergence than simple gradient descent. So this is the recap of everything that we have seen so far. So moving on, the topic for the day, we are going to look at these topics: divergences, normalizations, and various other tricks of the trade. So specifically, we're going to consider the following topics: the properties of the divergence and how we choose it. We're going to look at batch normalization. We're going to look, and now dropout, which is, these two really should be, the order here should be changed because we're going to look at batch normalization first. Dropout, gradient clipping, data augmentation, and other hacks are going to be in the extra lecture that I will record afterwards. So questions, anyone at this point? Any questions?
Nothing on chat.
Nothing on chat. Okay. So if there are no questions, I'm just going to keep bludgeoning on. So remember this, right? Now, let's start off with looking at the divergence. The loss we minimize is typically some constant times a constant plus the average divergence of the training instances. So effectively, the loss we minimize is the average divergence of the training instances. And this divergence has the property that it's minimum when the network output, which I have representing as YT over here, is exactly equal to the desired output for any training instances. So long as we do have that property, if our optimization algorithm actually finds the minimum, we will find the right solution, the best model for that particular data. However, the convergence of the gradient descent algorithm depends on other properties of the divergence, like how it behaves away from the minimum. Ideally, as you go away from the minimum, the divergence must have a shape that results in a significant gradient in the direction of the optimum. At the same time, as you approach the so this will sort of guide the algorithm towards the correct solution. At the same time, as you approach the optimum, you want the gradient to become smaller so that the updates become more careful and are more likely to arrive to stop at the correct solution. So here are some desiderata for good divergence functions. Ideally, the divergence must be smooth and not have any poor local minima. So if the divergence function here, this is these plots are showing for some hypothetical function, the divergence as a function of the parameter value for some parameter. And if the divergence function is something like this one over here, this is a no-no. The gradient descent will simply not work over here. Now, so you want divergences which are more like the ones to the right. But even here, there are issues. When you're far away from the minimum, you want the gradient descent to progress rapidly, reducing the distance to the minimum in big steps. But when you're close to the minimum, you want the algorithm to be much more careful, taking smaller and smaller steps so that it actually converges to the minimum. This means you want the gradients to be large, far away from the minimum, but small, close to the minimum. So rolling this back to you guys, of these two objective functions, which one satisfies that condition? Can anyone tell me? Anybody?
The blue one on the right.
The blue one on the right, right? So because what will happen is right here, if you have a divergence function of this kind, then it has a global minimum, right? It looks a bit like a flower. But then the slope here is very small. So because the gradient update steps depend on the slope, you're going to take tiny steps arriving to the minimum, taking a very long time. And then when you do get to the minimum, something nasty happens. The slope, it suddenly becomes steep. So now the step becomes large. And because it's large, you're going to overshoot the minimum and you're going to begin oscillating. So this, while it does have a global minimum, this is going to require a lot more tuning and tweaking of your learning rates and the learning rate schedules to assure you of actually arriving at the minimum. Because if your learning rate schedules are even slightly off, even though gradient descent should technically get you over here, you won't converge. You're going to go to bad places. On the other hand, if you have something like this, even a careless learning rate schedule is actually going to bring you here, because far away from the minimum, you have steep slopes, so you're going to take large steps. And then as you approach the minimum, the slope sort of keeps decreasing. And so the steps will get smaller and smaller and smaller. And it sort of assures you that you're going to arrive at the minimum. So we agree that this is the kind of shape we want. Now, can anybody think of situations where even the kind of additional requirements that we have in addition to a shape like this? So for example, if I were to compare a cubic and a quadratic, both of them have a bowl shape, right? If I were to draw a cubic function, I mean, if I were to compare a quadratic and a fourth power. So if I had x, and if I have say x squared is going to be something like this. If I have x raised to 4, that's going to be something like this. Which of these two is the better objective function? Anyone?
Quadratic function.
The quadratic, right? Because both of them have the bowl shape. In the case of x raised to 4, it becomes too flat near the minimum. And now your steps are going to become tiny, right? And getting here is going to be an immensely painful thing. So in some sense, the quadratic is your ideal objective function. It satisfies the requirement of being sufficiently shallow at near the minimum and sufficiently steep far away from it, which is why for most analyses of gradient descent and convex optimization techniques, we use the quadratic function as some kind of our standard and compare everything to it. So we've seen there are several different divergences you can use. You've seen two different divergences over here, at least two different divergences in the class. One is the L2 divergence, one is the KL divergence, right? Of the L2 and the KL divergence, which of them is, first, are both of them convex? Do they satisfy this property?
Yes.
Oh, okay. You're saying both of them are convex with respect to what? Over here. With respect to what? You should be able to tell me, right? There's a variable. What is the variable I would have to have on the x-axis for me to claim that the function is convex? What are the variables here? Anyone?
Sorry, y, the output?
Yeah, y, the output. It's the only variable you've got. D is fixed, isn't it? So that's going to be a quadratic. And say you want outputs in this range, 0 to 1. And you might have, for example, a KL looks something like that. Quadratic looks something like this. So now, this is with respect to y, right? But then let's consider a single perceptron or a softmax. And let's say I have only two inputs, right? And I'm going to assume that there is no bias just for convenience sake, just for illustration sake. And now we have our z, and then we have the activation function. Say this is a sigmoid, 1 over 1 plus e raised to minus z. And this is our y. We have the desired output d, and then we compare the two and we compute the divergence. This is how we did this, remember? So when I speak of the convexity over here, what are the variables out here? Anyone? What are the variables in this figure?
The weights.
And what are all the things you would be computing? This is a function of the weights, right? And this is a function also of the weights. So when you're actually doing any kind of minimization, you compute derivatives going down. Is that right?
Yeah.
Okay. So we agree that both the KL and the L2 are convex with respect to y. The L2 something like so, the KL may be something like so, both are convex with respect to y. What about z? Is it going to be convex with respect to z? Okay, skip z. What about the w's? Is it are both of them going to be convex with respect to w's?
Not necessarily.
Not necessarily. So I'm going to give you the answer. One of them is convex with respect to w's, the other is not. Can you take a guess as to which is which?
KL is convex with respect to W's.
Absolutely right. KL is convex with respect to w's. And this is your L2 divergence. It actually looks like that ugly function that I just showed you. Looks like a flower. It has a unique minimum. It's just not convex, right? Whereas the KL has this nice bowl shape with respect to the W's. And so, which is why this makes a lot more sense in the when your output layer is a softmax or a sigmoid than this guy does. Make sense to everyone?
Could you explain why the KL would be convex with respect to the weights and L2 won't? That part wasn't very clear to me.
So you can work this out, but remember, how do we actually, we have, what I'm doing over here is computing, wait, so the KL is going to be log of 1 over y, right? Which is going to be log of 1 plus e raised to whatever, wz. So this, if exponent is a convex function, you have the plus 1. The log doesn't quite compress it fully because of the plus 1. It doesn't, and even if it did, eventually you'll just end up with wz, and wz, you know, is linear, so it's convex, right? So this whole thing, I'm not sure what happened to my mouse. Something strange has happened to it. Okay, so this, I hate laptops. Okay, you get the idea. This guy's convex, and then I have a 1 plus, so you're going to end up with convex stuff. Now, okay, so here's the story so far. Gradient descent can be sped up by incremental updates. Convergence can be improved using smooth updates. And the choice of divergence affects both the learned network and the results. And most interestingly, just because your divergence function is convex with respect to the output of the network does not tell you anything about its behavior with respect to the parameters of the network. So the results can be non-obvious. In the case of a simple sigmoid, the KL is obviously the divergence of choice. One can sort of extrapolate and assume it's going to be that way all the way through. So let's start here. Here's your first poll. For those of you who can't see the poll, here is the poll. This is the first of these polls. There are 2 questions. So I'm going to stop this in 5 seconds. Yeah. So the answer is this. The KL divergence is convex with respect to the weights of the final softmax layer. The L2 is not. And for the second question, both KL and L2 actually have a unique minimum. It's just that although they have unique minima, only one of them has got the kind of structure where you can actually be a little more careless about your learning rate schedule. Let's move on to the second topic of the day, covariate shifts. Now, when we perform mini-batch descent, one of the assumptions we make, so in fact, why don't you guys tell me, what is the primary assumption that we make when we perform mini-batch descent? Anyone?
That the covariance matches the distribution.
The assumption that we are making is that if you randomly sample from the training data, then the distribution of the samples in the mini batch matches the distribution of the samples in your training data itself, right? You make that assumption. And that's where all of the analyses about variance and such likes actually comes up. So you're assuming that if you have a general layout for your training data, if each of these patches represents one mini batch, you assume that all of the patches lie in pretty much the same region of the space. In practice, that's not what's going to happen. Each mini batch will have a somewhat different distribution as illustrated here. So in other words, each mini batch is going to have a covariate shift with respect to the other mini batches. And this shift could occur this is not just for the inputs. This could be because this translates into the network. This is going to hold true for the output of every neuron in the network. And in fact, these shifts across mini batches can be very large. So mini batch training, which assumes that all mini batches are similarly distributed, can get badly affected by this variation across mini batches. So one solution to this is to shift every mini batch of the data back to a standard location so that now they all at least lie in the same region of the space. But then there are a couple of questions. Where exactly is the standard location? Because all you have are these mini batches, right? And secondly, how exactly do you shift each one of these mini batches? How do you estimate that? It's complex, so we're going to break it down into a two-step process. First, we're going to move all the mini batches down to the origin and scale their values such that each shifted and scaled mini batch now has a mean of 0 and a unit variance along every component. And then from this location, we will have a standard shift of the mini batches into a standard location in this manner. And we call this entire process batch normalization. The mini batches were shifted to the center, normalized, and that the normalized mini batches shifted to a standard location. And once you're done with this, all of the mini batches now lie in the same region of the space, and your mini batch descent will behave in a much more repeatable and respectable manner. So this process of batch normalization often ends up being quite critical to training your models. Now, the way we implement batch normalization, remember, this business of the shift between mini batches occurs not just at the input, it occurs for every neuron. So regardless of which variable you consider within the neural network, that variable is going to suffer this kind of shift. And so we usually implement batch normalization as an adjustment, a covariate adjustment that happens right after the affine combination of the inputs, but before the application of the activation. Although in practice, yes, Chris? What's the question?
Right. So I was wondering whether what informs the decision to after normalizing all batches to point of origin, what like informs the decision to move the distribution of all the batches to some other location?
We're going to see that in the next few slides. We're going to that in the next few slides. That's exactly what this whole business is about, right? And so,
We have a question on the chat, a student is asking, why do we need to shift the mean back away from 0?
So if every single parameter ends up at exactly 0, then you end up with 2 variables less to actually estimate. So you don't necessarily have to shift things away from 0. You're going to end up with fewer parameters. Remember, you started off with everything being in a different location. You lost that information. This is sort of recovering some of it. If you didn't do it, then the whole process would still work, but you're going to be worse off simply because you've lost some degrees of freedom in the process. You're just reintroducing some of those. Answer your question?
Yep, thanks.
Okay. Okay. So now, so going back, we generally sort of implement Batchnorm right here after all of these terms are added, and before the activation. And the final shift and scaling, which go from here, which transfers the mini batch from here to here, the location of the shift and the amount of scaling is actually going to be different for every single neuron, and it's going to be performed individually on each mini batch. And now remember that the process of batch normalization as we did it is a two-step process. So first, we sort of normalize all the instances in the mini batch, where we first subtract the mean of the mini batch from the instance and then divide by the standard deviation, so that all the instances in the mini batch now have, the mini batch now has 0 mean and unit variance. So then every instance is then scaled by some term gamma, so that you expand the distribution to the right size and then shift it to the correct location beta. And as you will see in a few seconds, this beta really, it's pretty remarkable. If you think about it, the shift is irrelevant. It doesn't really matter. The only thing that matters is the scaling. Now, that's because the neuron actually has a bias, and that shift beta is indistinguishable from the bias. So the only real Batchnorm parameter that you're left with is the gamma term. And the process of batch normalization itself can be shown in this manner. It's a two-step process. The first is the normalization of the instances in the batch, which is this guy. And the second is the shift of all of these instances to the right location in the space. Now, as far as computation is concerned, to perform batch normalization, we will need the mean and the standard deviation, the mean here and the standard deviation of the instances for each mini batch. So the first, given a mini batch of instances, now this entire set of operations is for a single neuron, okay? You would first compute, if we've decided to apply batch normalization on these z values, you'd compute the mean of the z values for the entire mini batch. Subsequently, you also compute the variance of the z values for the mini batch. And then we do the normalization, where we subtract the mean and divide by the standard deviation, the square root of sigma squared plus epsilon. This epsilon term is primarily required to ensure that you don't have a division by 0. This gives you the normalization of the u values, and then the u is shifted. These equations in white are performed over the entire mini batch. These equations in yellow are subsequently performed on every single instance within the mini batch. So here are all the operations. First, we compute the mini batch mean, then we compute the variance, and then we use them to normalize the z values for all of the instances in the mini batch, and then which gives us the normalized value u. Keep this notation in mind. And then we scale and shift that u to give you the repositioned z value, z hat. Now, yeah, there's another poll. Let's see. This is poll number 2 on slide 30 for those of you who can't see it. This is a simple question. Let's stop in 10 seconds. All right. So clearly, this is actually done over mini batches, right? That was the whole point of it. Now, here is a better picture for how batch normalization is performed. This is how I showed it right now. It's a two-step process. First, you compute the normalized U for every Z, then you compute Z hat. Actually, this is a better one. From each Z, you first compute the normalized U, then the U is multiplied by a gamma, and then you add a beta to it to compute Z hat. And then once you get the Z hat, you actually apply the activation of the neuron to Z hat. And now observe something over here. This summation beta is indistinguishable from just adding a bias to the Z hat term over here. So in other words, this shift for the batch norm is identical to the bias that goes into the activation, which is why when you actually perform batch normalization, you don't need an additional bias term for the neuron because the shift in the batch normalization already accounts for the bias. Questions, anyone? Anything on chat?
No.
Okay. So now this business of batch norm actually ends up causing some grief. Now, traditionally, in the usual training, the mini batch loss for any mini batch is the average of the divergences for the individual training instances in the mini batch, in the conventional training. And the divergence for any term is a function of the output of the network in response to that input and the desired output for that training instance. And so the divergence basically only depends on that specific training instance. The derivative of the divergence with respect to any parameter is also now an average of the derivatives of the divergences for the individual training instances. And these derivatives are can be independently computed for every single training instance. If we use batch normalization, does this get influenced? Anyone? How would this get influenced? So here's a simpler question. Can we now is the computation of the derivative for any instance independent of every other instance within the mini batch? Can they be independently computed?
Not quite.
What do you mean by not quite?
I guess I need to be more specific. No, because we're going to have to handle for the mean and variance that was for when it was shifted.
Absolutely, right? So here is the situation, right? The outputs are now functions of the mean and variances, which are functions of the entire mini batch. So if you want to represent it correctly, the output of the network in response to any input is the output of the network in response to that input and the mean of the mini batch and the variance of the mini batch. And so the actual, so this means that, and now the mean itself is a function of not just that instance, but also of all of the other instances in the mini batch. And so if you write the divergence more explicitly, this is the relation we get. The mini batch loss is again the average of divergences. The divergence for any training instance is a function of the output of the network for that input and the corresponding desired output. And the output of the network in response to any input is a function of the input, the mini batch mean, and the mini batch variance. And the mini batch mean is a function of both the current input and the remaining inputs within the mini batch. And so also the variance is a function of, now it's a function of the mean and the current input and the remaining instances in the mini batch. And so this actually ends up being quite a hideous function. And we have to compute the derivative of this more hideous function. So let's see how we can compute the derivative. And to see this, let's consider the dependencies at a single neuron. Now, within any neuron, if you consider all of the affine values Z within a mini batch as a single collection or a single vector, then batch normalization can be viewed as a vector operation that operates on the collection of these Z's to compute their normalized and shifted versions, Z hats. So this means that every z affects every z hat, and every z hat is affected by every z. And this is this combined operation that we actually have to deal with when we are computing derivatives. So more explicitly, let's expand out the operation and compare them to the figure we originally had to the back for the batch norm. The batch norm has two steps. The first computes the, for the first step here, normalizes the entire mini batch. And the second then shifts the normalized instances within each mini batch, right? So if I decompose this, the first component and only the first component is a vector operation, because this normalization actually considers the mean and the variance of the mini batch. The second operation which is the shift of the instances, is now performed independently on each instance. You basically just multiply the instance by the u value by gamma and then add a beta. So this is the entire batch norm operation, 2 stages. The first is a vector operation, where it's a vector operation over the entire mini batch. And the second one is a collection of individual scalar operations. So this means that when we are computing our derivatives and we are performing back propagation, we can compute the derivative with respect to each of these UIs individually, because each UI, once it's computed, is processed independently. And then when we actually compute the derivatives with respect to the z's, we have to consider the vector nature of the operation. So first, let's see how we would compute the derivatives with respect to the UIs. Here is the forward pass again at a single neuron for a single training instance in a mini batch. The neuron, of course, receives a set of inputs from other neurons. It computes this affine function z. And you, again, remember, we don't need to consider the bias anymore over here, because this bias is taken care of out here. So it computes this affine combination z. And then the first stage of the BN computes the normalized u for z. And then the second stage shifts the u to this new location, z hat. Now, during back propagation, as you compute your derivatives backward, you would initially have obtained the derivative of the loss with respect to y. We can multiply the derivative of the loss with respect to y by the derivative of the activation function at the current value of z hat, and we will subsequently obtain the derivative of the loss with respect to z hat. So this portion is very simple. Now, the real interesting portion is now the derivatives going backwards. Now, first let's consider what happens in the second block over here. In the second block, we have this very simple operation. We have z hat. We already have a derivative with respect to z hat. Then we had z hat was beta plus gamma times u, right? Beta and gamma are learnable parameters. So we need the derivative of the loss with respect to beta. And you can see from this directly that this is simply going to be the derivative of the loss with respect to z hat. So this is taken care of. We need the derivative with respect to gamma. And again, looking at this equation, you can see that the derivative of the loss with respect to gamma is going to be the derivative of the loss with respect to z hat times u. And we can also compute the derivative with respect to u. The derivative of the loss with respect to u is similarly going to be the derivative of the loss with respect to z hat times gamma, right? So you see where this comes from. This is fairly straightforward. And so we get the derivatives for the learnable parameters of the second stage. And we also get the derivatives with respect to the u term. And so in the process, we have managed to compute the derivatives all the way back to this u for every single training instance within the mini batch without considering the remaining training instances. Now, the real challenge is to propagate this derivative all the way back to z so that we can compute the derivative of the loss with respect to z. Now, for this, first we have to draw the complete set of dependencies between Z and U. Can you guys help me draw the dependencies? So within a mini batch, this is for a mini batch, right? I have Z1, I have Z2, I have Z3, and so on. I have U1, U2, U3, and so on. So what are the dependencies going to be like? What other variables are here?
All three of them affect all of the U's.
But what are the other variables? What is the actual nature of the dependency? What are the mini batch parameters?
The gamma and
The gamma is specific to the neuron. I'm speaking for the mini batch, for the transformation from Z to U.
oh, the mean and the variance.
The mean and the variance, right? So I'm going to have the mean and the variance. And what are the dependencies now?
All of them affect both.
So all of them affect both. And let's draw the complete lot.
And then both of those affect all of the others.
So both of those affect all of the others. And of course, you also have this guy, right?
Oh, yeah.
Is there something missing here? Does the mean affect the variance?
No.
No.
What's the formula for the variance?
Oh, yes. Sorry. Yes. Yes, it does.
So you have this connection as well, right? This is the complete set of connections. Now you can see how this.
Quick question.
Yeah.
Oh, if we connected Z1 directly to U1, shouldn't we also connect Z2 directly to U2?
Yes, I haven't drawn all of them.
Okay, cool.
So the actual set of dependencies is going to look like this. Right? Make sense? And now, questions, anyone? No, okay. But then there's more, right? Each of these U's within the mini batch affects the mini batch loss. So if I want to compute the derivative of the loss with respect to any given Zi, I have to sum over all of the U's. And so the derivative of the loss with respect to any Zi is going to be the sum over all of the U's times the derivative of the loss with respect to the U of the derivative of the loss with respect to the U times the derivative of U with respect to Z. So you're going to get two kinds of derivatives on this side. You'd get the direct link, but you also have to consider these cross links like the derivative of U2 with respect to Z1. Now, when you're performing backprop, this first term we've seen already computed. So the really painful bit that we're left with is the computation of the derivatives of these U's with respect to the Z's for every combination of U and Z. So you need both the derivatives for these direct links, but also the derivatives for these indirect links. And the two are different, right? So let's first consider the derivative in the case of the direct link, right? Again, in terms of derivatives, can you guys help me write out what are the three, I've already given you part of the answer. What are the components of these derivatives? If I had to, oh shoot, did I move this guy off? So help me with this. I want to write the derivative of the U by dz. Is that right? Let's say du1 by dz1. How many terms will it have? Anyone? Yes, Chris?
Someone on the chat says 3.
Yeah, I already gave you the answer. Can you tell me what those 3 are? First, why are there 3? Can you tell me by looking at this figure?
In the influence diagram, we only have the mean, the sigma squared, and the Zi going
Okay,
in.
is it always going to be 3?
For this scenario, yes.
Not necessarily, but we'll see why. Right? Because if I've got this guy, okay, let's consider this one with respect to this one. What are the 3 components?
It's the U. Well, there's one component that's just du dz, right?
That's a partial with respect to dui with dzi, right?
Yeah.
What's
And then
what's the second?
there's du d sigma squared d
Partial of u with respect to sigma squared and
d sigma squared dz.
is that a partial or a full?
That is a partial.
Would it be a partial? Remember, that is going to look at these two guys. How many paths connect these two?
Just one, then it's full.
So because it had two paths connected, you have this guy, but you also have this path, right? Between
so
sigmas,
there's a
right?
partial.
So the partial would only consider this path. Whereas you want to see the entire connection between these two guys. This has to be the
full.
The full. That makes sense? The full is considering all paths between these two guys. The partial is only considering this direct one. Right? What's the third term? Anyone?
du d mu dz.
It's this guy. Is that again? That's a partial, right? Because u is a function of three guys, right? So the partial with respect to mu b and the full, in which case they're the same. Here the full and the, which is going to be d mu over dz. So your derivative is going to actually have these three components. Will that make sense to everybody? Here it is. This is the first one, right? The partial of u with respect to z, which is the direct link. Then the derivative component contribution through the mu, which is the partial of u with respect to mu times the derivative, full derivative of mu with respect to z. And then third one, which is the partial of u with respect to sigma squared, and then the full derivative of sigma squared with respect to z. Questions?
Nothing on chat.
Okay. I'm going to work this out, okay? So here is the complete set of derivatives, and we're going to work out every one of these terms. Let's consider this first term. Which of these three connections is this first term referring to?
The
Going back.
direct from z to u.
The direct one, right? And can you tell me what that value is going to be? So we are speaking of this term, this connection over here. Look at the formulae over here. And which of these formulae applies to compute this derivative?
It'll be 1 over this square root of sigma squared plus epsilon.
Yeah, this is the connection. This direct connection is given by this formula here, right? And so u equals z minus mu over this square root of sigma squared. So that derivative is simply going to be 1 over square root of sigma squared plus epsilon. The plus epsilon is only to eliminate underflow. And so I can replace this guy by that formula, right? Now let's consider the second term here. What is this derivative going to be?
1 over b, because we're doing a averaging here.
So the u over mu, Aisha?
It'll be the negative of the same thing, negative.
It's the
1
same
over.
term, right? This is where it's coming from. The connection between u and mu is given by this guy. There's no u out here. This is the function that relates u and mu. So that derivative is going to be from here, minus 1 over sigma b squared, right? Square root of sigma b squared. Everybody see that? And so I can actually, yeah, here's a poll for you guys. This is the third poll out here. Is it? Yes. This one, yeah. There are two questions.
Yeah, I actually waited for you to finish talking before releasing the poll.
Yeah, no, it's a good thing you did. So you've got 5 seconds. All right. So here is the fun thing. The normalized value for u of u, which is z hat for any z, depends only on the remaining z's, but it doesn't depend on the u's. Remember this picture over here? So, wait, no, where is this? I'm not sure what happened, but if you remember this picture here, the u depends on all the z's. There's no connection, direct connection between the different u's. So this guy depends only on the z's. And for the second term, of course, this is a vector operation over the entire mini batch, as we just explained. So now going back to this du, the partial of u over with respect to mu, we just computed that term to be this one here, so I can plug it into the equation. We are left with the second term. And can anyone tell me what d mu over dzi is going to be? Which formula does that come from?
It comes from the generation of the mean, so it'll be 1 over b.
That's from this equation, and that's going to be 1 over b, right? And so we have computed this term. Let me plug that in. Easy enough. Now, what about this term? What is this term going to be? Anyone? Which formula does it come from?
The third one, but it's really hard to compute, I guess.
So how is it hard to compute? That's easy, right? Here's what I've got. I have ui equals z minus mu times sigma squared plus epsilon raised to minus half, right? So what is the derivative of ui with respect to sigma b squared from this formula? Anyone? Can you tell me what it's going to be?
Negative 1/2 times z minus mu b times 2 to the negative 3/2. So, yeah.
Minus negative 3/2, and is it going to be 1/2 or minus half?
It's just going to be -1 because you have to do the inner chain.
No, this is with respect to sigma squared.
Oh, sorry. Then yes, -1/2.
Right. So there you go. Easy. That wasn't so complex, was it? And so I've got this term that gives me the derivative for this connection. Now I need to compute. So I've got this term. Let me plug it in. Right. Now I need to compute the derivative for this final term, which is this, the derivative of sigma b squared with respect to zi. And let me hide this over here, although I've given you the answer already. But if I want to compute the derivative of this block with respect to this one, what is the formula? How many different components will this derivative have?
2.
And what are those?
From sigma squared to z, that is del sigma b by del z, and the
That's
one
going to,
via
is that a direct, or is that a partial or a full?
that's a full.
Full?
That's a partial, sorry.
That's a partial, right? And what is the second term?
Del sigma by d sigma by d mu.
Partial or full?
That will be a partial, sorry.
Doesn't really matter anyway, because there's only one connection between the two, right?
Mm-hmm.
It's only when you have multiple connections you have to vary between partials and fulls. If you ever had this confusion, if you ever had any confusion of the difference between a partial and a full, when you draw the influence diagram, if you have multiple paths between two variables, partials are not the same as fulls. If you have only one connection, the partial and the full are the same. Okay? And then what is the second term here?
Del mu by del z.
Easy,
that
right?
is a full, yeah.
That is, yeah, partial full is the same thing. And so this guy is going to have this term here, right? And now what is this first term? Sigma, derivative of sigma squared with respect to zi. Anyone?
That's 1 over B.
Is it 1 over B?
It should be 2 over B times Zi minus.
Oh, yeah.
That's correct. 2Zi minus mu B over B, correct? Beautiful. So we've done this. What about the second term? Sigma squared over mu B. Where will that come from?
It would be the negative of the previous derivative.
So that's going to be the negative of, are you sure?
It's going to be minus 2 over B, Zi minus UB.
But there's no specific Zi, remember? There's no specific Zi. It's with respect to mu B. So what are we missing here? This is going to, the summation will not go away. You're going to have the mu is going to retain the summation times 2, there's a minus, times the summation never went away, Zi minus mu B, right? Because the derivative is with respect to?
Yeah, that's right.
Right, so what is this value going to be? What is this guy? What is the sum of all the centered Z's?
0.
The
Zero.
standard deviation.
Wait, no, there's no square. This guy, when I subtract the mean from every instance, and then I sum the lot, what will you get?
Yeah, the 0.
That's a 0, right? And so this term simply becomes a 0, which means I don't even need to worry about this. I don't even need to worry about this guy because I know this term is a 0. And so the derivative with respect to sigma with respect to Z just gives you this one little term. I can plug it here. I'm not actually going to spend a lot of time on going through the details, but there's a very interesting little point that comes out of all of this. Let me sort of compact it all. And this is the derivative for the through line. The derivative of any given ui with respect to Zi, which also has the direct line, right? But now let's consider the case of the cross connection. In the case of the cross connection, how many terms will you have? Anyone?
2.
Just 2. It's this path plus this path, right? And so this derivative is basically the same as what you had for the through connection, except without the direct line. And so this is identical to the I equals j without the first through term, so you can just write out the formula from the previous slide, no big deal. Now, writing both cases together, here is the formula we get. The derivative of any uj with respect to any Zi is given by this formula here. When j equals I, it has 3 terms. When j is not equal to I, it has only these last 2 terms, right? Now, so remember, the reason we went through all that painful derivation was because we wanted to compute the derivative of the loss with respect to any Zi. And that was the sum over all of these guys of the derivative of the loss with respect to u times the derivative of u with respect to Z. And there's a reason I actually went through the arithmetic, and I'm going to give you the final formula. Let me write the entire formula out here. Here's what we get. This again is the derivative of uj with respect to Zi. When j equals I, it has 3 terms. When j equals doesn't equal I, it has only the last 2 terms. The derivative of the loss with respect to any Z is this summation. So when I write this guy out, I can separate this first term out for only the j equals I term, right? Observe that I'm summing over all of the j's. The derivative of the loss with respect to any Zi is being summed over all of the u's, correct? So this summation includes the direct connection and the indirect connections. And the only difference between the direct connection and the indirect connections is this one term here. So if I write this first term out separately, the rest of these summations are over the entire mini batch, okay? You can sort of ponder over the equations a little bit, but that's not the key piece. The key piece is this, right? Let's assume that all of the instances in the all of the instances in the mini batch are identical. What is this term going to be? Does anybody want to take a look and tell me? If all of the instances in the mini batch are identical, then every Zi equals every Zj. So what will this term be? Will the mean be different from the Zi's?
No, it'll be 0.
No. So this becomes 0, right? What about this guy? What is this guy going to be? Are the UJs different?
No, they won't be.
So this loss can come out. So this second term is going to simply be d loss over du divided by the square root of sigma b squared. And there's a 1 over b, but then the summation over b, the b's will cancel out, right? So this term is going to become the same as this term, is it not? I can write it out.
Yeah.
Yeah, I mean, it's got to be obvious, right? So what is the net derivative? This term became 0, right? So if all of your training instances are identical, the derivative of the loss with respect to every single Zi in the mini batch becomes, what does it become?
0.
What happens to backprop? Can it continue from there?
No.
Backprop got blocked. It died, right? So what if the mini batch instances, the variation was really very small, or the variance was small? You're going to have the same effect, effectively, especially if your loss function is smooth. So in other words, batch normalization will kill backpropagation if there isn't sufficient variation between the instances in the mini batch. Did that make sense?
Yes.
Right? Because what happens is the derivative of the loss with respect to the Zi's becomes either 0 or so small that you cannot actually continuing further makes no sense. And so batch normalization is best used. For batch to be and to work, you need diversity within the mini batch.
Can I ask a quick question about that?
Yeah.
Oh, sorry. We have a poll.
I'm going to relaunch it. Sorry, go ahead.
I was just wondering, if we're using multiple batch norms, like I can tell, like initially we can test the test data whether it's enough variance, but how about in the middle of a network when we have, you know, many layers? How do we know that the variance is being maintained throughout the network?
So remember, what batch norm does is that it modifies it modifies the variance of each mini batch to be unity, and then scales it by gamma, right? So can you look at gamma and tell me how this is going to work then? If gamma is very small, what will the variance be? Remember, if gamma was 0, what would it be? So you have this, right? You have Z hat equals gamma U plus beta. Ignore beta, right? So what is the variance of Z hat within the mini batch? That's going to become gamma squared, right? So within each instance, if gamma is very small, you're going to have very small variance, but that's only for a single instance. What this is, and so if all of your gammas are very small, your variance is probably going to be very small. But again, every neuron gets inputs from many other neurons, so you'd have to, there are a few more considerations than that. Anyway, let's take the poll. Yes, Shams?
Yeah.
So in the beginning, we said that because of the different distribution of the mini batches, we do this batch normalization. So what if we like normalize the inputs and, you know, like shift them to a standard location? So then we don't have to worry about all of these calculations.
So by the way, this is this very nice. The problem is, if you do that, right, you're still sampling that training data across many batches. So what you're really trying to do is to account for the variations across many batches. And that doesn't go away. Any global operation on the training data is not going to eliminate the variation between the many batches. The answer here, of course, is true, right? Did that answer you? Shams?
Yep.
Okay.
Thank you.
Right. So let's continue. Now, BN eliminates covariate shifts by normalizing out mini batch variances during training, but what about during inference time? So we don't generally operate over mini batches during inference. If you did, then you could just get the local mean and variance of the test mini batches on test data and use those to adjust for the covariate shift. But if you're operating on individual instances, you're not going to be able to compute means and variances, right? And so instead, we'll compute the means and variances for the individual mini batches and compute the average mean of these mini batches and the average variance of the mini batches. Specifically, for the variance, we will actually use this unbiased estimator, which uses b minus 1 as the denominator rather than b, and then use these terms to normalize the individual test instances and then shift those. That's during inference time. Now, BN, questions? Anyone? Okay.
We had a follow-up question about the variation in a mini batch. I guess you like sort of answered it. So if the variation in a mini batch is very small, will it cause the gradient to vanish?
Yeah, you just saw that, right? Yeah. And so again, remember that if the variation is very small at the input, it doesn't mean that the variation is going to be very small at intermediate neurons. What it will mean is that the variance is going to be very small at the first hidden layer. So you'd end up having trouble, you'd almost certainly end up having trouble computing the weights for the first layer. And it's possible that you'll also have trouble downstream. Anyway, Batchnorm is a neuron-wise operation, so we don't need to apply it to every neuron in the network. We can apply it to only some layers or even to only some neurons. In general, it improves both convergence rate and network performance. And empirically, people have reported that Batchnorm eliminates the need for dropout, which is another regularization technique that I'll talk about in my second part of this lecture, which I'll record offline. Now, to get maximum benefit from BN during training, the learning rates must be increased and the learning rate decay can be faster because things are being normalized. And again, as I mentioned, it works best if the data within each mini batch are sufficiently diverse, otherwise it can actually end up blocking derivatives from backpropagating. This means you need better randomization of the training data for BN to be effective. And here is a typical result that the original authors of Sergeyev and Zegedy had when they first published Batchnorm. This dotted line is what you get with standard stochastic gradient descent, mini batch training. If you use Batchnorm, you can see that the training converges way faster, and you also end up with much better classification performance. And so here's the story so far. Gradient descent can be sped up by incremental updates. Convergence can be improved using smooth updates. The choice of divergence affects the learned network and the results. And finally, covariate shift between training and test may cause problems and can be handled by Batchnorm, right? So, questions?
Nothing else.
Okay. Another very important fact.
Professor, I had a question.
Yeah.
So if we use a dropout and Batchnorm together, does that end up being detrimental to the performance or training?
So I haven't actually looked at the math too carefully, but intuitively it would mean that one of them is going to increase the variance. So yes. I mean,
Okay.
the two are going to be at cross purposes, right? So in some sense, yes. But I might be BSing. This is what is reported, right? Okay, here's something. Another very important problem is data under specification. And all the pictures I've shown you this very nice picture where I have said we have this function, we have these training samples, we're going to fit the function in all of these training samples. And when we do that, it's going to learn the entire function. Is that really true? The way we did it was we sort of defined a divergence function between the actual function we want and what the network actually computes. We average the divergence over all of the training samples. We minimize this guy, and we hope we learn the entire function. What could end up happening is something like this instead, where the network exactly learns to fit just these training instances and completely messes up everywhere else. And even this figure is wrong, right? To give you an idea of why this figure is wrong, look, on this little segment of line, I've already drawn 5 training instances. You will never, ever, ever, ever get such a density of training data. What is the real density of training data you're going to get? So consider a trivial example, right? Let's say you're working on 100-dimensional binary inputs. That's a tiny image. It's a 10 cross 10 image where every pixel has only 0 or 1 value. So it's really tiny, right? And so you have 100 binary values. There are 2 raised to 100 possible combinations of these pixels. So there are 2 raised to 100 possible values that your input can take, 10 raised to 30 possible inputs. And each of these inputs is only going to lie on the corner of a hypercube. So if I give you 1 trillion training instances, you're still going to be, the number of training instances is still going to be off by a factor of 10 raised to 15 compared to all of the corners of the cube where we are trying to compute the function. Make sense? Questions? So I want you to understand the magnitude of this. If I just had only a 100-dimensional input, and this is trivial, it's binary, then the 100-dimensional binary input, all the possible inputs live on the corners of a 100-dimensional hypercube. And if I want to specify the function fully, I must specify the function value at every one of the corners of this hypercube. That means I must specify the values at 10 raised to 30 corners. If I give you 1 trillion training instances, 1 trillion training instances is going to be off by a factor of 10 raised to 15 in the amount of data that you need to specify this, fully specify this cube. To give you a better idea, even on this tiny example, let's say each of these edges were some finite length, and I just put you in a tiny spaceship and landed you in some random corner of this cube. And I said, just travel along the edges of the cube and report to me when you find a training instance. The universe will end before you find your first training instance. That's how far away you're going to be from the first training instance. That's how sparse your training data really are. Or to give you an even more dramatic illustration, if I were to logarithmically scale this back and find out the number of training instances per dimension, remember this is a 100-dimensional input, you're going to get, if I gave you 1 trillion training instances for this tiny problem, nobody ever gives you 1 trillion training instances, and problems are never this tiny. You're going to get something like 1.000001 training instances per dimension. So in effect, I'm asking you to find an entire function, but I'm giving you only 1 point to do so. And say, okay, here's this point, find me the function. And you can see that this is really absurd, right? And this doesn't even begin to make sense. So given this, is it even reasonable for us to expect that the network will learn something useful? Anyone?
No.
Doesn't make sense, right? This is just, I mean, our data are too sparse. And even assuming so this means you need some severe additional constraints to fill in these missing regions acceptably. And so let's take a look at this from a simple binary classifier. So I have this classifier, and I want to build a classifier. The training data consists of these red dots and these blue dots. In this ideal situation, I would learn this blue curve, which computes the a posteriori probability of the classes. But then the neural network is a universal approximator. It can end up simply learning these training data perfectly and just give you this purple curve instead. Which of these two is the better option? Which do you want the network to learn? Anyone?
You want the smoother one?
You want the smoother one, right? This makes no sense. You don't want the purple curve. So why can the network actually learn the purple curve? Let's go back and take a look. The network can end up learning this purple curve because the perceptrons in the network are individually capable of learning these extremely sharp rises and falls. And the reason they can do so, now just is this: consider a single perceptron with just a sigmoid activation. It gets worse with other activations, right? Now a sigmoid activation can look like this blue curve. It can also look like the red curve. The larger W is, the steeper the sigmoid activation is going to be. And when W becomes infinite, the sigmoid activation is essentially going to just become a step function, a Heaviside function. You see that? Questions, anyone?
None on chat.
Anybody else? So you see why this happens, right? If you allow the weights of the sigmoid, or any activation really, to be arbitrarily large, that function can end up capturing extremely steep variations. And if every function, every neuron in your network is capable of modeling such steep variations, now the network can end up learning this function. So the way to prevent the network from learning this function is to make sure that each one of these neurons is incapable of modeling something so steep. Guys, I'm going to go 5 minutes over as usual. Please bear with me. So how would you prevent the neuron from learning something so steep? Anyone?
Limit it so that it can't go more than some value.
You limit the W, right? You constrain the W to be low. That's going to force the perceptrons to learn smoother, slower varying functions. And so that's what we're going to do. Here's your standard loss function. If you simply minimize this loss function, this is unconstrained. Instead, what we will do is to add the second term over here to the loss function, which is the squared norm of your weights for every single neuron. And when you minimize this augmented loss function, it's not only going to minimize the divergence, it's also going to try to make sure that the weights are small and that the functions therefore that it learns end up being small. And the amount of importance that you assign to learning small weights is going to depend on this regularization parameter, lambda. And so when you actually add this extra term, it makes a very trivial change to gradient descent. You'll be taking the derivative of the augmented loss, which means that each divergence term is now, to each divergence derivative term, you just now add just lambda times the weights itself. So the derivatives now become not just the derivative of the divergence, but also the derivative of the divergence plus the weight itself. And this is what you're going to use within gradient descent. Now there's one more final way. So this is just the pseudocode for how you do it. Let me skip that. So this is the last topic. There's one more final way in which you can actually smooth the network output. And this is through network structure. It turns out that we can get constraints from the structure of the network. For a given number of total parameters in the network, deeper networks impose more smoothness constraints than shallow ones. Why? Because each layer works on the output of the previous layer. And so if any layer smooths a function, the next layer is working on an already smoothed function, it's only going to smooth it further. And so here in this network, if the first layer learns this ugly function, red function, the next layer operates on this guy and it's going to learn something smoother, like this green function. And the next layer is going to operate on this guy and it's going to learn something even smoother, like this blue function. Again, this is provided that the individual neurons are also prevented from learning very steep rises. And so this, just rearranging your parameters to have deeper rather than wider networks is going to give you smoothness constraints that kind of help. To see how bad this actually gets, let's take a look at this example. So in this case, I'm trying to learn a simple binary classifier. This one is trying to learn this classification boundary. This one's trying to learn this guy. I want a 1 output in the white regions, a 0 in the black regions. And we know the optimal architecture for this problem. This includes a square and a triangle. So I need 7 neurons in the first layer, 2 in the second, and 1 output neuron. Similar thing out here, right? So if I start off with the optimal architecture, then I generate like 1,000 samples from this decision boundary, and then train the network. And I use every known trick to mankind to train the network. Here are the decision boundaries that gradient descent will actually learn. It's complete rubbish. Nothing like what you really wanted to learn. So this is the first thing that you learn. If you have a network whose structure is optimal or close to optimal, you're guaranteed not to be able to learn the parameters of the network properly, because you really made the problem very complex. You have to over-parameterize the network. You need more parameters such that just through random learning, some of the neurons will learn to do the right thing. That's step 1. Step 2, now let's go and take a look at the issue of depth. Here, I tried to learn 2 different decision boundaries. One is this hexagon, the other is a decision boundary in the shape of a bear. In each case, we've drawn 1,000 training samples. And now we've got an over-parameterized network. This network has, I'm using 660 neurons in each case. Here, I've arranged the neurons in 3 layers of 220 neurons each. Here, it's 4 layers of 115 neurons. Here, it's 6 layers of 110 neurons. Here, it's 11 layers of 60 neurons each. And do you see what's happening? If I rearrange the same number of neurons in terms of depth rather than breadth, as the network gets deeper, it's able to learn the structure better and better for the same amount and the same training instances. Same thing over here. As I rearrange the neurons to be, the network to be deeper and narrower, it's more able to learn this decision boundary than the shallower but wider networks. Another thing you can do is to have more training instances. And with 10,000 training instances, you just capture the depth. So the final thing we saw today was that data under specification can result in overfitted models. And these must be handled by regularization of the weights and by more constrained, generally deeper network architectures. So I'll stop here. If you have any questions, I can take them. Otherwise, thanks for listening. Rashmi, you can stop recording.
Yeah.